Hello, everybody. Welcome to Falcon High School Chemistry Podcast 9.2. We're in Unit 9, The Nature of Gases, and this is Miss Gray, and I am joined today by Mrs. Uy. So, hi, Mrs. Uy.
Hi everybody, how are you doing guys? I hope you're going to enjoy watching this podcast 9.2 that we're going to have for you.
And we're pretty new at this, guys, so bear with us and be forgiving of our mistakes.
Yes, please.
I think we'll probably make a few for you to laugh about. Let's get this back. Oh, see, now I'm going through the whole thing. I told you we'd make a mistake, and there you just saw one right off the bat. Let's see. Going back to that slide, here's what we're going to do today. We're going to talk about intermolecular forces. Oh, drawing straight lines is hard.
That's fine.
And we're also going to talk about changes in states of matter. This, I think we've talked about before in our first semester of chemistry.
I think I remember that.
Yeah, we talked about solid, liquid, gas.
Gas.
And we also talked about two other phases that are not very common. We talked about, what was it, Bose-Einstein condensates,
Yeah.
when you get really close to 0 Kelvin. And then we also talked about plasma.
Yeah, plasma.
Right, but we're not going to worry about those. Just the three common states
Oh,
of
good.
matter. I know, we're going to do less complicated.
Yeah.
So for today, let's look at liquids and gases. Liquids and gases take on the shape of their containers, and solids have their own shape.
Their own shape.
But liquids and gases are not quite the same, because gases expand to fill up whatever container we put them in. But a liquid does not. It only fills up as much as what we put in there.
Yeah.
That's how we can measure with a graduated cylinder, right? We pour it in there and it only fills up to a certain line.
Which is not hard to do.
Yeah.
Right.
So let's see. If we had a graduated cylinder, then we would have like this long tube, and it has markings on it up the side so that when we pour in our liquid, we can see how high does it fill up. Remember, gases will fill the whole container all the way to the top. So if we don't put a lid on it, they'll keep going
They'll
because
keep going.
they don't know that this is their container if there's not a lid on it. They'll just go outside too. But our liquid stays where we put it.
Yes.
And let's investigate why. What are the particles doing in there? So let's switch to this screen where we have some particles of gas.
That's
floating
cool.
around. Right, so we have a closed container, which is really important. If we don't close our container, then the gas particles just fly out. Do you want to see? Look, if I open the container, our gas particles start to fly out. Well, I better close it again before they all escape. All right, so our gas particles go bumping around, and suppose we add some heat. Oh, look, my drawing's still there. Whoops, let's get rid of that. Bye-bye, drawing. Okay, so let's add some heat and see what happens to our gas particles when we add more energy to them. What do you notice, Mrs. Uy?
I think they're moving so fast.
Right, they started to move faster.
Yeah.
And what if we remove some heat? Oh, whoops, go this way. There, hey, look at our ice underneath.
There's ice in there. That's really cool.
Yeah,
Now
so,
they're moving slower.
right, and I saw on our temperature, on our thermometer over here, the temperature went down,
Yeah.
and they move more slowly, and the temperature goes up, they move more quickly. Well, in podcast 9.1, we talked about how adding energy is adding heat, and it makes the particles move faster.
Move faster.
That's the kinetic molecular theory. So our students just learned about that.
Wow.
Let's look at a liquid and see if it moves the same as our gas. Here's our liquid particles. And wow, they're moving.
They're moving. Can you see
Barely.
that they're moving? Yeah.
Let's turn on the microwave, because this is inside a microwave, which means that there's a wave of energy passing through. And this is how you heat up your food in the microwave. You send a wave of energy through your food, and it disrupts these molecules. And right here, our legend says these are water molecules. So when you heat up your food in the microwave, if your food doesn't have very much water, the microwave doesn't work very effectively to heat it up. Right? Have you ever tried heating a piece of toast or something in the microwave? It starts to get really weird.
Yeah.
Yeah. So now I just turned the microwave off. That means our energy's not going through here anymore. And our particles
You can't
starting to
see
slow
wave
down.
anymore, right?
Right, it's a flat line now.
Okay.
So how is this different from the way our gas particles moved? They were moving fast when we put energy through. Was it the same speed as our gas? Let's go back to our gas. Oh, I went past it. Oops. There's our gas. The speeds don't seem to be all that different, but we added some energy to our microwave. So we'll add energy here.
And now they're moving so fast.
Right, now they're going fast. And these guys are going pretty fast too.
Yeah.
But our liquid particles seem to be more crowded.
Yeah,
Don't you agree?
it is.
Yeah. I wonder if we could like, hold them still and count how many particles. Because that would make a difference, right? If we had more particles, they would be more crowded. More moles of gas would be more pressure
More
because they'd
pressure,
be more crowded. But if we counted these particles, I think I have more gas particles, quite frankly.
Yeah.
Yeah, there's a lot more particles
Mm-hmm.
in here. They can't see me pointing. I pointed at the screen, everyone, but you didn't see my finger.
Yeah.
Yeah, so I think gas particles don't move in the same way that liquid particles do.
Mm-hmm.
They bounce around a lot more. They move more randomly.
Yes.
And when they bump into each other, they just like bounce away.
Mm.
But let's look at the liquid particles over here. Our liquid particles seem to interact with one another for a longer period of time, especially in the times when we have the red particles bump into a blue side of the particle, because the red hydrogens are positively charged and the blue particles are negatively charged, oxygen and hydrogen, you know. Oh, I didn't get my pen. I thought I had my pen. So this side is negative, right?
Negative.
And the other side, I can't catch it. It's positive.
It's positive. So the red one is positive.
Yeah, because it's hydrogen, and they don't get to have the electrons as much as the oxygen does.
Yeah.
Oxygen's an electron hog. But let's go back to our slideshow and see what were we talking about? Why do gases expand to fill their containers?
Yes.
Because their particles don't stick together as much,
Mm.
right? So as they collide, they just bounce off one another.
Yeah.
But as liquid particles collide, they stick
They
together.
stick to each other. Yeah.
Right, and that's how we define solids, liquid, and gases. That gas particles are described as having no attraction between the particles. The attractive force is essentially zero for a perfect gas. Writing with this pen is always a trick. No attraction for our gas particles, but our liquid particles have enough attraction between them that they stay in their container and they don't go flying out like a gas would.
Yes.
But for a solid, we have the most attraction, and that's what holds them into a shape of their own. A solid has its own shape. We don't have to give it a shape. Like your desk is not going to pour into another container, right? So a solid has its own shape because these particles have the highest level of forces, attractive forces between them. And then, so we have no attraction, and here we have the most attraction. This would be somewhere in the middle.
Somewhere in the middle.
Good. Oh, I always forget to clear off my writing before I go to the next page. It looks funny. So phases of matter will be then defined as a balance between intermolecular force and kinetic energy. So if you have a higher intermolecular force, or IMF, then your phase will be more solid. And if you have lower IMFs, then you have more like a gas.
Yes.
And there's a balance between them, where if we add kinetic energy, then we can change how much force is in between them. So what is an intermolecular force?
Yeah. What is it? It's in your paper, guys. You're going to read it over there.
Yep,
There's intermolecular forces, IMFs.
I sure hope they're following along in their note-taking packet.
I think so.
They
I think they're following.
Okay, so IMFs, look at this part of the word, molecular. And molecular means a molecule. Here's
Molecule.
a molecule of
Hydrogen.
hydrogen chloride.
Mm-hmm.
And inter, like the interstate highway, means it goes between two molecules. So from one molecule to another. Intramolecular would be right here, the bond between two atoms in a molecule.
Hydrogen and chloride.
Right, and that's called intramolecular,
Okay.
right, because it's within the molecule. But we're looking at intermolecular, so between two molecules, not within one molecule. Gosh, behave yourself, little pen. Between two molecules is the intermolecular force. One of these days, I'll have an amazing pen that does exactly what I wanted to do.
Yeah, we're waiting for that.
Okay, so what would happen if we added heat to these particles? Then they would start to move faster,
Mm-hmm.
right? And as they move faster, then they would probably move farther away from one another.
From each other.
And if they're farther away from one another, then that attraction between them gets less.
Okay.
It would be lower. So let me clear this writing so we can see. This line between them is between the hydrogen and the chlorine, because remember I said before, hydrogen is a positive,
Okay, yeah.
and chlorine
Chlorine
tends
is
to be very electronegative.
Negative, yeah.
Right, it's an electron hog, like oxygen.
Mm.
So that's why these would be attracted, because opposites attract,
Oh, yes.
right? But if we spread our charges farther apart, it's like taking two magnets and putting them farther apart. It weakens the attraction
Yes.
between them. So in essence, we're saying the more kinetic energy there is, the lower the IMFs will be.
Mm-hmm.
And for gases in particular, move that out of the way, for a gas, the kinetic energy is large enough to overcome all the IMFs. So we have no IMFs left in the gas, and they have no attraction for one another, those particles, and they just bounce around
Each other.
Yep, and they never stick. So there's our gas particles again. So they never stick to one another. They just bounce right off and keep on colliding with other things. In fact, the gas particles in the air right now are colliding with you in your body about 1 billion times a second.
Oh, wow.
Yeah. Okay, well, let's move on then and summarize what we know about the relationship between intermolecular forces and kinetic
energy.
Okay, so here's a very common picture of gases and liquids and solids. And let's look at water, because I think most of us are familiar with water.
Yeah, we are.
We've seen water in all three phases before. We'll start with liquid water, right here. Liquid water, like raindrops.
Yes.
Okay, if we take some of the heat away from our liquid water, then it turns into
solid
water. We usually call this ice.
Ice.
But I drew a snowflake because it's pretty.
Yeah.
Okay, well,
although we're in spring right now, but
yeah, I bet we get more snow though this week.
Oh, really?
They predicted it. They forecasted it.
Oh.
Yeah. Everyone's praying for a snow day, but I think they forecasted it for Sunday. Sorry, guys.
Oh.
I know. Bummer.
It's okay.
Yeah. And I said that I drew this snowflake. It wasn't my drawing. I took it from somebody else. All right. Then what happens if we add energy to our liquid water?
The liquid water will turn into vapor?
Right. Then it turns into a gas.
Into a gas.
Right? And when we have a gas that's normally liquid at room temperature, then we call it vapor.
Vapor.
Right? Other gases like nitrogen and oxygen, hydrogen, right? They're gases at room temperature too. So they get to be called gases all the time.
Okay.
But a vapor is something that's normally liquid at room temperature.
At room temperature.
And we would call that a vapor. So all vapors are gases, but not all gases are vapors. Well, let's look at what happens to this process. Here, I got to get my clicker. First, we talked about freezing, right? That liquid water would turn into solid water, and that process is called freezing. And this term applies to any liquid that becomes a solid. That's called freezing. What if a gas
Mrs. Gray, are they going to write down something? Tell me what you're talking about? I think so.
I think they should. And if you and I talk too fast for them, and they can't keep up with us in their notes, then they can push the pause
Oh,
button
yeah,
on
that's
the
the good
podcast.
thing about this, right?
Right. That's one great thing about a
Yeah.
podcast is
All
that you
right,
can hit
guys,
pause.
start writing down now. Listen to Miss Gray and start writing.
Yep. So you fill in with your own words. You don't have to use my words.
Yes,
Or you can look in your book. I don't care as long as you have a good definition,
exactly.
right? So condensation. Can you give us an idea of that, Mrs. Uri?
Condensation is when water vapor
Okay.
or gas turns into liquid water.
Right. Exactly.
Yes.
So for any substance that's in the gas phase,
Mm-hmm.
in order for it to become a liquid, we're going to have to get rid of some of the energy within the particles.
Okay.
The particles themselves have to lose energy so that they can slow down enough to stick together and become a
Yeah.
liquid.
And look at that blue arrow. It means heat energy release, right?
Yes, exactly. So
Yeah.
anytime we go from right to left,
Mm-hmm.
that means we have to release energy
Energy.
from the particles themselves. And that means the air around it, as we're going from gas to liquid, the air around it is going to get warmer,
Yes.
but the particles themselves get colder.
Yes.
Right. Let's look at this crazy term, deposition. Oh, I hit the wrong button. This button is what I wanted. Deposition is when a gas becomes a solid without ever being a liquid. That's pretty rare for water to do that in Earth's atmosphere.
Okay.
That doesn't happen very often for water, but it's pretty common for carbon dioxide. That's why we call it dry ice, because it never becomes a liquid,
A liquid.
not at regular temperatures.
Okay.
And dissolving is not really a phase change. Have you ever made Kool-Aid at your house?
Oh, yes.
Yeah?
Yeah,
I love
I
Kool-Aid.
love that. Yeah.
Especially tropical punch. That's my favorite.
Oh, I
It's
haven't
the
tried
red.
anything about that. I
Yeah.
haven't tried that one yet.
It's a good one.
Yeah, okay.
So dissolving means we're going to stir it into the water,
Mm-hmm.
and all the solid particles get mixed in so much that we can't see them anymore.
Yeah.
And all of our students just learned for net ionic equations that we call these things that dissolve in water aqueous,
Yes.
right?
Aqueous solution.
And to be in aqueous solution means it breaks apart into ions.
Ion.
It has to exist as charged particles,
Yes.
right?
Mm-hmm.
So that's what we're doing. Like when we stir salt into water, the salt breaks into
Two ions.
ions of sodium and ions of chlorine. So
Plus.
to dissolve, we have to break the bond that existed between these two. Yeah, that's supposed to be a plus sign and
Positive
a
and
minus sign.
negative.
Yeah. So we have to break the bond that was between these two. And to form a bond, it takes energy. To break a bond, it releases energy.
Yes.
So all of these processes that we've just described are processes that release energy. So in other words, what's happening when kinetic energy is lost means that the IMFs are going to be, what do you think, formed or broken?
Broken. Is it broken?
I disagree.
Okay.
Because we're going from liquid to solid,
Mm-hmm.
we get bigger forces.
Oh, yeah.
Does that make sense?
Gotcha. Yes.
It's okay to guess wrong, as long as
As long as I'm being corrected.
Yeah. Okay, so we
Thank you, Ms. Gray.
increase the IMFs between the particles as the kinetic energy is lost.
Okay.
I bet you won't get this wrong again.
Yes.
Yeah, because
I
now
will. Yeah.
all the students heard you mess up.
Uh-huh.
They hear me mess up all the time too. Okay, let's look at some other processes. Here's three more: melting, vaporizing, and subliming. I know we changed that, but we didn't. Oh,
No.
this matches what's in their notes too?
Yeah.
Oh,
Yeah.
good. They're going to like that. So everyone knows what melting is. That one's easy, right? If you're going to
Yes.
melt something, that means we're changing a solid to a liquid,
To liquid.
right? So that's melting. And then vaporizing,
Or vaporization.
right, vaporization is either evaporating it, or if you want it to go faster, you boil it, right? Evaporate. Wow, this pen is so disobedient. It gets all out of control. It's not my fault.
It's the pen's fault.
It's the pen's fault. That's what my students say. I didn't mess up, it's the pen.
Yeah.
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 Okay, so when it evaporates, I know where they get it from. That means we're changing from a liquid to a gas.
To a gas.
Okay, and then subliming or sublimation.
Sublimation.
Right, this is a process that doesn't normally happen for water. Where we
Just
go-
like deposition, right?
Yeah, the opposite of deposition. Go from a solid to a gas without ever being a liquid. And we use the example of carbon dioxide. This is the process that our students see in that fog machine or whatever. When the dry ice turns into that smoke, right? It's just now big fog and smoke. Wow, look, it's going crazy, my pen.
Pen likes that.
Yeah, I made it mad. I lost my clicker over here. But what we see happening is it goes from solid to gas.
To gas.
And it's never a liquid.
Okay.
So that's sublimation. Now, I wonder, how do I get my clicker back? I have to redo, reset. Oh, that's not the one I want. Because I don't think it works the same way. So now we have to click through this again. No big deal.
It's okay.
My
Going
students
back
are
again.
used to me making mistakes. Okay, so now all of these processes that we just described, these three are processes that are going to add energy, right?
Yes.
To melt something, we have to heat it up. I want this clicker first. Now I get my pen. So as the kinetic energy is increased, then before, when we lost kinetic energy, we increased. Oh, look, my pen is green now. What happened? We increased IMFs to lose kinetic energy.
Okay.
So now, if we are gaining kinetic energy, that means we decreased the intermolecular force because the particles move farther away and now they can't stick together as well.
Oh, yeah.
Decreasing the IMFs. All right, I think we got that. So we're cruising right along. Let's describe what happens when water boils. Everyone thinks they know this because we've all boiled water to make our macaroni and cheese.
That's very simple thing.
Yeah, right? And so it seems pretty simple, but we want to make sure they understand the chemistry of what's happening here. So the very first step is evaporation. The first thing that happens...
Write that down, guys.
Yep, the first thing that happens is that the liquid changes to a gas. And evaporation is a process that occurs at the surface of the liquid. So that's just going to happen. You don't really have to make it happen, right? But if we turn up the heat on our water, it will happen faster. So the evaporation occurs at the surface of the liquid. And liquids evaporate faster when we add more heat. Because that increases the kinetic energy and they move faster and bump together more. But if we have enough kinetic energy, then we're going to break the IMFs. What does IMF stand for?
Intermolecular forces?
Yes, intermolecular forces. So we're breaking IMFs between the particles. Good. The next step is that the liquid molecules change to the gas phase. And this is going to create vapor pressure. Is this screen too hard to read? What do you think over there, Shannon? Can you read it? Okay, you can read it? Good. And she's sitting like halfway across the room. So if Shannon can read it, then we're good to go. But Shannon knows all of this stuff already because she's in AP Chem. She's a master at this. Oh, yeah. Okay, so the vapor pressure is going to increase. We learned in podcast 9.1 that vapor pressure means just above the surface of the liquid. There's particles of that liquid that became a gas, and the more particles there are in the gas phase, the higher the vapor pressure. Right? So as more of the liquid turns into gas, our vapor pressure increases. But we don't consider our liquid to be boiling until the vapor pressure is equal to the atmospheric pressure. So let me get my black pen because I don't like the green. Those of you who are really liking the green pen, sorry. I'm going to draw a picture In fact, I think I need a new page. Oh yeah, this, well, let me do it. Let's try it a different way. Add a blank slide. Because I want us to be able to see what's happening here. So let's draw a beaker. This is our container, and we've got our liquid inside here. All right, so as the kinetic energy of these particles in here increases, then more particles will be able to escape the liquid phase
Yes.
and become gas particles. And these gas particles could just float right out of the container. But something else is pushing them down, and it's the atmospheric pressure. You see, there's air pressure around this container, and it's going to push down on the vapor that's being generated in the liquid. So as we form more of these particles, they can push harder. And once these two pressures are equal, then the water will boil. So we have to heat it up enough. Oh, there's our picture on top of our words. Here we go. We have to heat it up enough so that the vapor pressure is equal to or greater than atmospheric pressure, and that's when the liquid will boil. So what happens when you're at a higher altitude and the normal atmospheric pressure is already less? Then you don't have to heat it up as much to get it to boil, because the part that's pushing down and keeping it in the liquid phase will be less.
Okay.
So it takes less kinetic energy to break the IMFs and turn the liquid into a gas.
So you mean it's easy to boil water when you're at high altitude
Right,
than when
exactly.
you're in lower altitude?
So normally the boiling point of water is 100 degrees Celsius, right? But in Falcon, it tends to be closer to 92 or 93 degrees, which is easier to cook my spaghetti that way. Okay, well, let's finish up our slides with solids. We've talked about gases. We've talked about liquids.
Now we're talking about nature of solids.
Right. So that means, what are solids like?
Yes.
Yeah. Well, solids have their own shape. Because their particles stick together more.
Yes.
But there's two different types of solids. One type is called a crystalline solid. And this word crystalline comes from crystal. And if a solid forms a crystal, then it's considered to be a crystalline solid. We talked about this in the first semester too.
I think so. I remember that.
Yeah. So these particles are arranged in a regular repeating pattern called the crystal lattice. And it's the same every time for every kind of particle. So the one that I've shown here in the picture is, I think, magnesium sulfate crystals. If they were perfect little cubes, then we would suspect maybe they were sodium chloride. Can I draw a perfect cube? I am not an artist. My students are better at art.
It looks
than
like
me.
cube, Miss Bear.
Yeah? Thanks. Okay. You're being nice now. Here's some other examples. Besides sodium chloride, there's also granulated sugar. And granulated sugar is what most of us put in our iced tea or in our Cheerios or whatever, right? Just the normal table sugar. And copper sulfate, I think we used that in a lab before, maybe.
I think so.
I don't know.
Yeah.
But that makes a regular repeating pattern. So they have their own shape and they keep their own shape. It's hard for you to take salt and sculpt it into some other shape.
Yeah.
Right? That wouldn't work very well. But let's look at a different kind of solid. The kind that lacks an ordered internal structure.
What do you think is that?
That means it doesn't have a crystal, right? And so it doesn't have its own shape.
So you can form it into another shape.
Right, exactly. We call these ones amorphous solids. If I can spell this correctly, does that look right to you? We'll check later. Amorphous solids don't really have a shape of their own because they don't have a crystal structure. So these are moldable. They're still solids. Whatever shape we put them in, they'll stay that way. But we can do lots of different shapes, like wax in candles. You can form it. Plastic is a very common moldable material. We make lots of different things out of plastic because it can take on so many shapes. And then here's another one, glass.
Glass.
It has lots of different shapes that it can be. And here's one of my favorites. If you're decorating cakes and you want
Cake,
to make
yeah.
flowers and pretty shapes for your
That's
cake.
easy to form into a different shape, right?
Right,
Powdered
right,
sugar.
because of powdered sugar is in our frosting,
Yes.
and we use that to make different shapes. Powdered sugar is used instead of granulated sugar because the particle sizes are so small, we can mold it a lot better. Oh, and then this one, right here, calcium acetate. Some of our students used this in the stoichiometry lab.
Oh
that we just did.
yeah.
Calcium acetate.
Acetate.
Right, and we're going to use it in our next unit for an amazing demonstration called the flaming snowball.
Oh my God. Here's the word flaming.
Yes.
Students like that.
Right, and you're going to like it too.
Okay.
It will be kind of scary.
I'm looking forward to it.
Good, me too.
Yeah.
All right, so we have crystalline solids and amorphous solids. One important difference is that a crystalline solid has a definite melting point. It always melts at the same temperature. But an amorphous solid melts over a wide range of temperatures. So that's why wax tends to get soft first and then it melts. Because some of it is melting and some of it is not. And so it gets soft before it actually turns to a liquid. And we can move it around that way, right?
Miss Gray, you told me a
Yes.
while ago that this part of the podcast is very important because you said it will come out on a test, like essay
Oh, an
question.
essay question. That was before when we were talking about the boiling of water. Oh, where was that slide? I can't
I
get.
think it's good to remind them, right?
Yeah, I think that's a good point, Mrs. Uy. I'm glad you brought that up. Let's go back to that slide that they need to know because we've never asked them on a test an essay question before.
Yeah.
So this is the one. The process of boiling is going to be an essay question on their next test.
Okay.
And let's clarify what that means in chemistry because we don't want an essay that starts with an introductory paragraph and then has 3 body paragraphs and then a concluding paragraph.
We don't have time to read that long
No.
essay.
No, not that kind of an essay.
Yes.
This is just an extended written response where they have to know these 4 steps
Yes.
and explain them in order.
So,
I'm so glad you reminded me of that
yeah.
because our
I just
students
remember that.
our
'Cause
students
I
will be
love to
grateful.
write essay.
Me too. Me too. Just not too long.
Yeah.
Yeah. Good. All right, here's our last thing.
All right.
Phase diagrams. This is a graph that's going to represent the 3 states of matter for a substance, and we only talk about one substance at a time in a phase diagram. So
Okay.
just for one substance. And it's based on the relationships between temperature and pressure. And because the temperature and pressure vary so widely on a phase diagram, it's not going to be a graph with axes that are going up, like what they have to draw in math class.
In math.
They have to follow even increments along the axis
Oh.
or they show a break. Well, in a phase diagram, they're not going to see a break and they're not going to see even increments. Here's an example. See, as our pressure increases, then the temperature is going to increase on the x-axis. Yep, there's temperature and pressure. And the numbers that they'll see here are never going to be numbers that increase by the same amount every time. They'll see small increases here, and then all of a sudden it gets really big all of a sudden.
Yeah.
They would never normally draw such a distorted graph in math class. They would get in trouble for that, right,
Yeah.
Shannon? Yeah,
Yeah.
definitely big trouble. But in chemistry,
chemistry, that's
there's
different, yeah.
a reason we do that. Here's an example that we're going to do in class for this phase diagram. See how these numbers are increasing nice and evenly here. And are they doing the same thing here? Oh, finally.
No.
No, they goes from 30
Negative,
to
yeah.
10 is an increase of 20, then 20, 20, 20. Oh, that one's pretty normal.
Yeah.
Yeah, I bet we'll see some other examples where it's not even. But let's go back to this one so we can see what's happening. Phase diagram shows the 3 normal phases of matter, solid and liquid and gas. And any temperature within this range where it's at low temperature and low pressure is typically going to be in the solid phase, right? Low energy.
Yeah.
Yeah? And any temperature that's in the highest range, highest temperatures, things are in the
Like
gas
over
phase.
100?
For water, it
Yeah.
would be over 100
Mm-hmm.
degrees, right? But if our water is under greater pressure than 1 atmosphere, then
Mm.
it could be in the liquid phase, like let's see, 0.92 degrees, would be somewhere around here perhaps. Well, by straight lines. That's like in Falcon, where our pressure is lower, so it turns to a gas sooner.
Okay.
And then this line right here that divides the two represents what we call equilibrium, where both of them exist at the same time. So imagine you have a glass of ice water where you have both solid water and liquid water in the same container.
Yes.
Some of that liquid particles will be turning into solid particles because they get cold when they touch the ice. And some of the ice is turning into liquid water because they get energy from the particles around them.
Yes.
So we have both processes, melting and freezing, happening right here along this line. And for water, that tends to happen at 0 degrees Celsius. So this must be the phase diagram for water because our temperatures at 1 atmosphere match what happens for water. It freezes at 0 and it boils at 100 when we're at a pressure of 1 atmosphere, which is at sea level, right? The normal pressure.
Yeah.
And there's a couple of other points that we want to make sure our students know about and recognize. The critical point means once you heat it up, it doesn't matter how high the pressure is, it will never again be a liquid. So there's a certain temperature for every substance where when that temperature is exceeded, you can never have a liquid anymore, only a gas.
Okay.
So that's our critical
point.
This one, it doesn't look like is labeled. It's called the triple point. And it's rare to observe this for water, but for some other substances, we can observe at room temperature a triple point, where we have solid, liquid, and gas all together in the same container at the same time, because the particular combination of temperature and pressure allows for all three to exist at the same time. So that would be pretty rare for water. But for other substances, it's not so rare. It's much more common. And so we'll go over a phase diagram in class so that we can, wow, everything's writing from the first page. We want to make sure you can interpret a phase diagram so that you know this is the part that is a solid, right? Here's our solid phase at the low, and with high temperature, that's our gas. And then in the middle is liquid. Right. So we'll make sure everyone gets a chance to practice that. And I think that's it for our notes. And the next thing they'll see in their handout is a hint of what their homework will be.
Yeah.
Are we going to do the homework at home anymore?
If they still have time, they have to do it.
Sure.
Yeah.
Students are allowed to
Yeah.
do these problems at home. But our goal with the podcast is that the notes has now become your homework.
Yes.
You listen to the podcast at home. And then you get to do these problems in class, where you have our support and our coaching and our guidance and the support of your classmates too.
Yes, exactly.
Right? So you're allowed to do these problems in class, or you are allowed to do them at home.
If they wanted to.
You get to choose.
And if you have questions, then that's the time that they can ask.
Yeah, come to class and ask us questions.
Yeah.
And if anything that we've said today made you think of an experience you've had and you want to tell us about it, we'd sure be interested to hear.
Yes.
All right, that's it.
Because I know our students are very smart, Miss Gray, right?
They sure are. They make lots of connections that we never even think of.
And it's good to learn from them.
Definitely. Well, let's see. How do I stop this recording? We got to get our recorder. Wow, I've never seen that happen before. I'm kind of scared. There it is. That's the button I want. That's it for today, folks. Enjoy the rest of your day.
All right.